In my first video, we learned that all living organisms are made of nothing more than chemicals, with different arrangements of simple elements and with varying degrees of complexity. If you haven't watched it yet, I'll put a link in the description to it so that you can go do so, then come back and watch this one. In this video, we'll explore how you can get from simple molecules to the more complex building blocks of life, and maybe even make a basic protocell along the way. In 1924, Russian biochemist Alexander Oparin published The Origin of Life, a book outlining a series of steps for how living cells could arise from simple chemistry. His book was based on a scientific understanding of chemistry and biology, but lacked the experimental evidence needed to show that it could actually work. But in 1952, Stanley Miller and Harold Urey created a simulation of the Earth's water cycle filled with simple gases believed to be in the early Earth's atmosphere. They added an electric spark to simulate lightning, and after letting it run for several days, these chemicals naturally reacted together to form amino acids, including the ones that make up proteins found in every living organism, including you. This demonstrated the feasibility of the first step of Oparin's hypothesis. Since the Miller-Urey experiment, multiple scientists have simulated volcanic eruptions, meteor impacts, deep-sea underwater vents, each with various chemical compositions believed to be prevalent in the early Earth, and all have generated amino acids. We've even found these building blocks for life in outer space, implying that they can naturally form all throughout the solar system. As amazing as that is, this is where creationists tend to scoff and say something like,
"Amino acids? That's impressive, ooh."
You're not very bright, are you?
We're just getting started. To get to the space shuttle, we had to start with stone tools and work our way there. Rome wasn't built in a day, and the multicellular organism wasn't built in 6. In 1958, Sidney Fox discovered how a mixture of amino acids can spontaneously form into polypeptide chains as the mixture dried. He called these protein precursors proteinoids.
It's not even meaningful information as far as DNA is concerned.
No, that's because DNA and RNA are made of nucleotides, not amino acids. But in a number of the simulations mentioned above, scientists also observed the natural formation of nitrogenous bases that make up nucleotides when coupled with a ribose sugar and a phosphate group. We've been able to demonstrate the formation of the ribose sugar from naturally occurring chemicals as far back as 1861, when Alexander Butlerov discovered the Formose reaction, and the phosphate groups are demonstrably naturally occurring as well. But for years, despite having these 3 pieces of a ribonucleotide, scientists were stumped, trying to find the circumstances under which they could merge to make a fully formed ribonucleotide. But science doesn't just throw in the towel and resort to wild speculation, it keeps digging. Chemistry is complicated, and there's usually more than one way to skin a cat. Finally, in 2009, John Sutherland demonstrated an alternative chemical process that started with simple molecules and high-energy intermediates. Many of these were also products of the Miller-Urey experiment. By simulating precipitation, evaporation, and solar irradiation, they ended up with a fully formed ribonucleotide. Now we're getting somewhere. But how did these bond together to form nucleic acids like RNA? Researchers Jim Ferris and Leslie Orgel discovered that ribonucleotides naturally form into strands of RNA on the surface of montmorillonite clay, a common clay found worldwide and all over the ocean floor, when they dried and rehydrated the sample, a process similar to the rain cycle in shallow ponds or the rise and fall of tides. Additionally, RNA strands have even been found to polymerize on simple ice crystals. So we now have strands of free-floating RNA and polypeptide chains called proteinoids, but to get something resembling a cell, we need some type of vesicle to encapsulate all this. Experiments at the Simonite Lab simulating high-pressure, high-temperature hydrothermal vents found that fatty acids formed from hydrogen and carbon monoxide on the surface of catalytic minerals found below the ocean. As these concentrations of fatty acids build up in the water, they automatically bunch together on their own like oil droplets to form semi-permeable membranes with their hydrophilic ends facing towards the water and their hydrophobic ends turned in towards each other, capturing amino acids and genetic material inside their newly formed membranes. Inside these new little vesicles, scientists have discovered that free-floating ribonucleotides will automatically base pair with strands of RNA with occasional mutations. They're still trying to figure out how to get the backbone of this complementary strand of RNA to chemically bond this new strip of ribonucleotides together without assistance. But just because we're still looking for some pieces of this puzzle doesn't mean that the answer isn't out there waiting to be uncovered. When heated, these 2 complementary strands divide, copying the protocell's genetic material. If these strands of RNA aren't then surrounded with a sufficiently saturated solution of nucleotides to bond with them, they can fold in on themselves, forming a ribozyme. These ribozymes perform different functions based on their shape, which is determined by the order of nucleotides that compose them. Some ribozymes will automatically combine different amino acids together to make proteins. Others can tear proteins apart. And after examining hundreds of RNA chains, researchers at Simon Fraser University found ribozymes capable of building nucleotides from free-floating molecules surrounding it. In other words, they could build their own building blocks, although initially it did so rather poorly. But after just 10 generations of mutation and selection via PCR, ribozymes emerged that were really good at creating more nucleotides, which could be used for faster self-replication. These ribozymes were actually involved in the process of their own replication and increased their own odds of survival. So we now have a simple little protocell with genetic content, nucleotides, protein-making ribozymes, and a cell membrane capable of copying its genetic content and responding to natural selection pressures. There are a lot more steps and over 3.5 billion years to get from here to modern cells, but this simple protocell is already starting to blur the boundary between life and non-life, and each step occurred automatically in simulations of early Earth-like environments. But how does the cell divide? And how can simple, single-celled prokaryotes like this evolve into complex multicellular eukaryotes? I'll cover that in my next video. So make sure you're subscribed and hit that bell button so you get notified when I release it. And if you really like what I'm doing with this series, please consider supporting my work on a per episode basis over on patreon.com/holykoolaid. There are different perks depending on how much you pledge per video. While I've spent the last several years immersing myself in complex scientific topics, many of you know that I was raised in a young Earth creationist family, and when it comes to math and science heavy topics, I still feel like I'm playing catch up. It's healthy skepticism based in scientific literacy that inoculates us against the dangerous pseudoscientific claims of cult leaders or alternative medicine quacks. When someone starts spouting nonsense about the healing effects of quantum energy or vaguely invokes one of Einstein's theories to push an ideology or sell a product, what better way to counter it than with an actual understanding of the science? For that, I highly recommend that you check out this week's sponsor, Brilliant. Brilliant offers courses in everything from the basic physics of the everyday to Einstein's theory of special relativity, using visual representations of the topics. The best way to learn is by doing, and their visual problem sets are fun and engaging. Want to prove to a young Earth creationist that the Earth isn't 6,000 years old? They've got you covered. Are flat earthers driving you nuts? Why not calculate the circumference of the Earth? You can sign up for free to try out their basic courses, but if you're really serious about taking your science education to the next level, I recommend that you go premium and get full access to their entire library of courses. Go to brilliant.org/holykoolaid to sign up today, and as a special thank you to all my viewers, the first 200 of you who sign up will get 20% off an annual membership. Thanks, and as always, dare to be curious, but don't drink the Kool-Aid.